Hello there. Welcome to our today's science lesson. The topic for the day being communication. Maybe wondering, communication is a term mostly related to language. But no, communication is everywhere. And in fact, it is through communication that everything is the way it is in our world today. Now, in our previous lesson, we talked so much about measurement, the Bunsen burner, and all that is involved in the lab when an experiment or a discovery is being done. Remember, a discovery comes from an experiment. And we mentioned the things to do with the measurement, where we saw that there are various aspects that we measure in our lab. And in those measurements, we have units associated with those measurements. We looked at particular examples where we used volume, a measuring cylinder. We also looked at a thermometer where you measure temperature, and we saw how well you are supposed to go about doing the measurement, how you are supposed to orientate yourself in terms of the eye position to get the best reading of that instrument. Now, in that measurement, we got out the readings. And in the readings, we saw how best you are supposed to now record what you have been observing or reading. You record. And I remember having said that it is at the point of recording that either good work is done or a bad day can easily be found from the so much you have done. And out of the recorded information, analysis is usually done. Do proper recording, analyze the work done, then finally you can easily predict from the results you will have recorded and analyzed. And I gave an example of two levels or two sizes of crystals of sugar, a big one and a small one. You have done that experiment, you discover that the small crystals dissolve much faster than the big ones. But there's a part that you had not done. How about refined sugar? Very fine crystals of sugar. How do they dissolve? That was a prospect that one was to get. What were you expecting? And the answer came out to be, because of the experiment that one could have carried out of the two crystals, different sizes of the crystals but bigger in size, one can easily predict how the fine one will behave. And we predicted by saying that the fine one will dissolve even much better than the smaller crystals that we had used earlier. That is the advantage of doing experiments and doing proper recording, doing proper analysis of the recording you'll have done. But today, I want us to look at communication. And in this sense, I want to look at communication in terms of how well do you record your data? How well do you record your findings? How well do you record what you have observed? How well do you record what you have measured? In that recording is when you say you will be communicating. As you record, you will be communicating. How? Remember, whatever you do as a scientist now, or as a scientist wherever you are, you will have to make sure that the other scientists at the other part of the world, or scientists to come in the future, should know what you did. Probably, you are carrying out an experiment that you may not carry up to the end of it all. You may require somebody else somewhere or somebody else to come in the future to complete that good work you are doing. How does that scientist work on it if you didn't do a proper recording, if you didn't do a proper communication? So it becomes very helpful for us to know how to communicate by doing proper recording of our work. So today, our communication is in terms of how best are we supposed to record our work. There are various ways one can do this communication. That is, various ways one can do the recording of the work that has been done in the various experiments or areas you will have done your work. It can be in an outdoor lab or an indoor laboratory. But all in all, good recording must be done to communicate to other scientists. One of the best methods that is commonly used is the use of tables. So in the communication, one of the ways to communicate is to record the work, the observation, the data in the table form. So record data in table form. So you record any data in a table form. Remember, data can be in the form of anything as per the units that we have we mentioned in the earlier or in the previous lesson. One of it can be in terms of maybe length, can be in terms of mass, can be in terms of number, can be in terms of volume. And remember, each measurement you do must be in the correct units. Now, when recording this data in the table form, you have to make sure that each table has a correct and congruent, direct, understandable heading. The table can be in so many formats. For example, if you can have this one as a table, and maybe you are carrying out an experiment on 2 or 3 different issues, 2 or 3 or more, but at least more than one. But still, you can work with one and still tabulate your work in a table. Now, in the case you are comparing 2 or more things, then you have to clearly state what is where. For example, I can have in this table, this first column to have, let's say, cars. And maybe here I have lorries as 2 machines that I'm going to compare in terms of probably some aspects of interest. One aspect of interest can be in terms of, I look at maybe the speed. So I look at the speed in relation to cars, the speed in relation to lorries. I look at luggage, how heavy a luggage can any of these carry. Maybe the luggage, or let's say the mass of the luggage, this one can carry. We can also look at it in terms of maybe the shape. And looking at the particular aspect here we are looking at is speed. Speed now in relation of the cars. Then again the same aspect, speed in relation to lorries, and so on. Then you can give the figures. You can say the speed at a particular point. Remember, this speed, you don't just take the speed at any point. You have to locate at a particular point. For example, on a highway. Here is a policeman, a traffic policeman on a highway with a speed gun. And you will wish to know at what speed does a car or a lorry move at that particular point for it to be safe. So using your speed gun, you discover that the speed of cars is maybe 60 kilometers per hour. So the unit here we are looking at is kilometers per hour. So you discover maybe cars are moving at 60 kilometers per hour and lorries are maybe moving at 50 kilometers per hour. But now remember, for you to reach this 60 or reach at a conclusion of 50, you must have done some other arithmetics which can be found in another table. So you can have another table. You can have another table which will be having a particular heading of just particularly speed and the car, so that you can have maybe 20 different cars, record the speed of each car, then at the end of it all you make an average and maybe you find the average is coming to 60. So you don't just pick on one car and you say the speed is supposed to be 60. You have to make an average. To make that average, it means you are also having another table where you are going to record. So you can have maybe car 1, 2. So this one is car 1, 2, 3, 4, 5, 6, etc. Here, these are table, again, just like this one, but in particular for cars. And this car, you have to record the car and the speed at which it was moving. And also, we have maybe to go into further analysis of looking at what time. Is it during the day? Is it during a rainy time, a dry time? Those are different conditions. So you can say, for example, here is car number 1 during dry conditions and during wet conditions. Then you are looking at the speed. Maybe during the dry condition, it is moving at 67 kilometers per hour. Wet season, maybe, or wet time, it is moving at 59 kilometers per hour. Go to the second car, maybe it is moving at 65, and this one is moving at maybe 60, and so on. After you have done all of this, remember what you are doing is you are communicating data. The data you will have gotten on the road after observing the speed of these cars or of these lorries move. After that, you have filled all this. You can now make an average here. You get your average. You also get your average here. Then average 1 and average 2. You now have your average 1 plus average 2 divided by 2. Then you get your final figure, which is now being recorded at this point. What you are doing is communicating your observation for further analysis. So the same is done for lorries. You come to mass. Maybe you are on a highway, way bridge. Hope you have seen such a way bridge where you find that as a vehicle passes by, they have to get the real mass of that vehicle, so that probably they want to construct that road in a particular special way to hold or to carry very heavy luggages. What you have to do is you also have to do such a thing, such that you get so many cars, so many lorries, and probably again going by seasons. You can go by seasons, you can go by conditions. You record the masses of these or the weight of these vehicles as per that season. Then do the same calculation in terms of average, get the figure and come and record here. Maybe we get the cars are around maybe 1,000 kilograms or 1 ton. And maybe the lorries are giving us an average of 25,000 kilograms or 25 tons. This one can be gotten with a search. The same to shape. Maybe you want to see which type of vehicle is liked by most of the Australian Sydney dwellers. Sydney as a city. So you like to see which model of a lorry or a car is liked by most of the dwellers, so that you can increase its productivity or reduce the productivity. Maybe also to do further analysis and see why most of the people like that type of vehicle. Is it to do with the performance? Is it to do with the less pollution? Is it to do with the consumption of fuel? And so on. Or maybe even the color. You have to do such a thing. What you will be doing is you will be communicating. And maybe through this, you can even advise the government on what to do on some of these aspects. So tables are very good in communicating data of what has been observed in whatever venture one is doing, whether it is in a lab or like in what we have just seen here. This one cannot be done in a lab. This is something that can be done on a road, but it is very helpful. But it can only be helpful if what has been gotten can be communicated to the rightful maybe departments or to other people who may wish to do some more maybe tests or experiments or an addition of the same. Another way to communicate what has been discovered, what has been found, or what has been done to other departments or to other people or to other scientists is through use of graphs. So number 2, record data in, we had a table, so we have, you record the data, but in graphs. We record data in graphs. Now, looking at a graph in relation to a table, you may even discover that a graph is much better than a table. Because for a table, apart from the heading, as we have said, it has to be clear and the numbers, interpretation of the table may require a little bit more knowledge. So it will require somebody to have prior information of some issues, maybe to understand that table. But when it comes to a graph, it can be much, much easier for one to get to know what whoever did was trying to communicate. Graphs, as much as they are good, they don't just come in one format, like what you have seen for the table. They can come in different ways. Just like tables, graphs can also be manufactured in different ways. For example, in a computer way, you can come up with a table, but you can also come up with a computer graph. For a table, you can use a program like Excel, in Microsoft, ways of getting the table. You can get it in a Excel form, where in that Excel form, everything you want to do the table can be done. So the same can be done for graphs. And in fact, when developing the graphs, you can use different colors, different shades, different shapes for you to come up with the graph you want to communicate in a proper way, to give a proper information for whoever is to consume the information to understand it in a much better way. So let's look at the various graphs one can use to communicate data or information one has gotten. So among the graphs we can have is one is bar or what we call column graphs. Bar, or you can also call it a column graph, depending on what you like most. Bar or column graph. Now in this one, it independently shows a particular aspect of concern. This shows that you may be dealing with more than one aspect, more than one experiment being done. So which means more than one results have been recorded, and you will wish to show them in graph form, maybe for better view or for better understanding of whoever is to use the information. Now maybe the best way to describe this is to use a diagrammatic representation for us to understand each other. Now to understand the bar graph and column graph, it will be good to do a comparison of the two. We have the two at the same time so that we can see how each one of them looks like. So we are talking about graphs, and we want to look at bar and column graph. Now, when you look at a bar graph, the bar graph looks like it is an inverted shape of a column graph, or column looks like an inverted of the bar graph, but they all have the same shape, only that one is kind of an inverse or a slanting way of the other one. So the column graph looks upright. It's just like a column. You are creating a column, and columns always are vertically oriented. So you can have something like this for a column. So you can have columns. So as you can see, these are columns. To make them more beautiful and more easier for one to have a sharp interpretation of what you are getting, you can get them in terms of different colors or different shades. So I can use this. There we are with a column graph. But now that is useless if we don't critically look at what we are comparing or what we are talking about, because as it is like just a picture. But to create sense out of it, we have to label the graph. We have to show that this is a graph of this in relation to this. For example, we can talk about the number of cars, just an example, the number of cars that pass a particular point on a highway in relation to the month of the year. We have maybe 12 months, but we only want to talk about the first 4 months. The first 4 months of the year, January, Feb, March and April, the first 4 months of the year. Maybe there's a point of interest the government has to want to look at what to do on that particular road at that particular point. So you look at number of cars. Number of cars. So here we look at the number of cars, and that's on the y-axis. Then on the x-axis, we have the month. Month of the year. Month of the year. So we can have maybe J to stand in for January, F for Feb, March, and April. So at least with that, now one can easily read something out of this column graph. And even anyone who doesn't have much knowledge, if I give you that as a picture without telling you anything, you look at it, you may easily tell me that probably I've given you a wrong thing. Maybe I was intending to give you my photograph. Then you will tell me, no, what you have given me is this is a picture of something to show, yeah, it is talking about cars and the month. Then you can easily pinpoint out that it looks like the third month of the year, we have so many cars passing by that particular point, because you will have gotten a figure from the y-axis. It is showing maybe from zero number of vehicles to maybe, if you can talk of 10,000 vehicles at that particular point. You discover that during the third month of the year, you can have as high as probably, if you can put it at 9,800 vehicles passing by that particular point or on that particular bridge. But during the fourth month, the number drops so much to, let's say, maybe 2,000 vehicles passing through the same particular point. Because of such a data, which has been done what? Communicating. Maybe by the highway authority, you have communicated this data to the government. The government can easily set in a project or a finding to see how come just after a few days the number of vehicles drop by even more than a half. By so doing, something good will come out of that, and the government can even make good programs for each citizen with such data being communicated. If it was an experiment in the lab, this is not just on the road, as I'm mentioning, using the road, it can be even in the lab. Probably, you are trying to dissolve 4 different solids in one particular type of solvent by the name water. Then you look at it in terms of dissolving the so many crystals of the same mass. So many crystals of the same mass, but at different temperatures. At different temperatures. You can talk of maybe this one is at 10 degrees centigrade, 20, 30, 40 degrees centigrade. So having looked at the 4 different temperatures, levels of temperatures of comparison with the 4 different substances, it can be any type of different substances that are dissolving in the same type of solvent, same volume of the solvent, in the same conditions, apart from the condition of varying temperature. One can easily then say that this substance 3 can be any substance. Let's give it, for example, sodium chloride crystals, the common table salt. Substance 3 is more soluble than any other of those 4 substances at a temperature of 30. But substance 4 is less soluble. And maybe what we are doing to this is to find out which type of solute to be used as a solute to form a solution for a certain experiment under very high temperatures or under very low temperatures. Just like what we have in some saline areas, Like there's a place in a country in Africa by the name Kenya. There is a lake that is found in very dry conditions by the name Lake Magadi, and it is one of the best sources in the world of production of a substance called trona. Trona is a substance that is scooped from that lake during the day, but during the night when the temperatures are low, then sodium chloride is gotten. How do you get to understand such things? Such a type of experiments can be done to test on solubility of various salts in the same solvent, which is water, at different temperatures. So this one can be interpreted very easily using a column graph. Let's look at a bar graph in relation to a column graph. As I said earlier, they almost look alike. The only difference is bar graph, the bars goes horizontal, but the column, the bars goes vertical. So here we can have examples like maybe this. So as I said earlier on the column graph, by just doing what I've done, scientifically I can say I haven't done anything, because you cannot decode anything out of this diagram. But at least you can do it if we do a labeling. Let's, for example, look at accidents. Accidents are things that occur, and when they occur, one may need to understand the rate at which they occur during which times of the year. Maybe you want to reconstruct the road to fit the specifications so that to reduce on the accidents. But probably you also want to know during that time of the month which type of machine on the road. Is it a lorry? Is it a motorbike? Is it a car? Is it a bus that has so many accidents being involved with it? So we can label this as maybe this one is cars, maybe this one is motorbikes, this one can be buses, maybe this one is lorries, and maybe lastly we can even have bicycles, or maybe just to use bigger machines we can have pickups, just to have bigger machines on the table. But again, by doing so, still it doesn't make much sense. Is it car accidents? Remember, you will have given a heading here that car accidents in relation to vehicles and a certain type of the month. Just like even for this one, you will also have given a heading there stating cars in relation to month or solubility of solids in relation to temperature. So here I have also to specify something here. Car accidents, motorbike accidents, buses, lorries, pickups, in relation to which month? So you can say in relation to month of maybe December. Month of December. And you will have given figures here ranging from 0 to, let's say, maybe 1,000. So you discover that from this bar graph, you can easily pinpoint that buses maybe are the ones highly likely to be involved in an accident in the month of December than any other vehicle or any other. And maybe motorbikes are less likely to be involved in an accident in the month of December. Then one can easily want to know what could be the causative factor for this? Maybe one could have imagined buses are not supposed to be involved in accidents. But here data, if correctly and sincerely recorded. Remember I mentioned earlier in our previous lessons that in science, the recording must be done sincerely and correctly and immediately. So if this was done sincerely, correctly and immediately, then the data is reliable. One can easily try to correct himself or herself for having imagined that buses are maybe more comfortable than maybe personal cars, and so on. This shows that from the graphs, one can easily read out the information very fast without further thinking of it. But remember also, as what we did on the column graph, you can color these bars or shade them in different ways just to give a clear and precise appearance. Now, in addition to these graphs that we have already seen, the two of them, we also have others that we call bar graphs. So we are still talking about graphs, but now this one is a pie graph. A pie graph. That one was a bar graph. We have talked about bar graph. We have talked about column graph. Now we are talking about a pie graph. Now a bar graph is a little bit different from the way it is represented in relation to what we had already seen in the first two. For this one, we look at a circular shaped representation of a graph, and the circle represents 100% of whatever you are talking about. 100% of whatever you are talking about. It can be 100% of anything. Now take an example, or for example, the number of cows. The number of cows that you have on your piece of farm. The number of cows you have on your piece of farm are maybe 200. And you want now to look at these cows in relation to the amount of milk they produce. The amount of milk they produce. But remember, out of the 200 cows, which now represent 100%. So these 200 represent 100%. And 100% represents the whole circle. Represent the whole circle. So you want to know if these cows will all be producing milk or not in the month of January. So as you can see, we always go back to you have to be specific. Data must always be specific. So it is specific here. We are talking about 200 cows. We are also specific. We are talking about cows. But we are also specific on at what time. We are talking about during the month of January. So we want to see these cows. Are they all going to produce milk? If yes, then you can take the whole pie graph as a representation that we shade the whole of it and say, as you can see, we have shaded the whole of it, all of the cows were producing milk. But in case a fraction of these cows, a fraction of the cows are the only ones producing milk at full capacity. And maybe full capacity here we can say a cow producing between 30 and 40 liters per day, we shall term it to be at full capacity. Any that will produce less than 30 liters but more than 20 liters, so between 20 and 30 we say it is producing a half, and less than 20, we assume it is producing a quarter. So 20 and less, we take it to be a quarter. This one we take it to be a half, and this one we take it to be full capacity. We want to represent this information so that the owner of the farm can easily and very fast interpret the data and know if the production of his or her animals are to the best level expected. We can represent this information in the data. But remember, all these animals that are either in full capacity, half or a quarter, must total to 200. So, starting from the center, this is the line. If we shade the whole of it, then we shall have said, or we shall be telling the owner of the farm that all the animals are producing, all the 200 animals in the month of January are producing 30 to 40 liters of milk. But as we know, that cannot be always achieved. But on doing data recording, you discover that those that are doing full capacity are 120 animals. 120 animals. Those that are doing a half are 60. And the rest are doing a quarter. You need first of all to find out what is this the rest. So the rest means 200 minus 120 plus 60 gives you the rest. So that is 200 minus 180, which gives you 20. So a quarter here means only 20 animals will be giving a production of 20 liters and less. Now, to represent that information on the pie chart, you need to calculate the numbers in terms of percentage. In terms of percentage, or in terms of the angle. Because remember, this is 360 by angle. And 360 by angle means 100%. 360 by angle means 100%. So this one is the same as again 360 degrees. So we have to convert just like 200 into percentage, or 200 into 360 degrees. So if 200 gives you 100%, what will 120 give you? What will 60 give you? What will 20 give you? It will give you a percentage. Or you can go in terms of 360 degrees, and that one is in fact the best, whereby using a protractor you can easily get the best angles in this, then you shade to show whatever you want. So you can as well convert if 200 is equals to 360 degrees. How about 120? How about 60? How about 20? Now, roughly, if you can take that more than a half, so slightly more than a half, these ones are animals that are producing at the maximum expected. Then we have 60, which is slightly more than a quarter, because a quarter is 50. A quarter of that is 50, because 200 is 100%. So a quarter of that, which is 25%, is 50. And 60 is slightly above 50. So a quarter is this way, so you can have it at that point. Then you can use this one. You can use different colors to represent that. And the rest, we can now shade it using this. Now from here, it is good to label, because if I give you such a drawing without any other wording, then it comes out to be a useless drawing. But to make it useful, data must accompany it. In addition to the title, that the pie graph of the production of milk for 200 animals. Production of milk for 200 animals. Best producers 30 to 40, average 20 to 30, and less than 20. With such information and having labeled now this, then it gives us the sense to interpret the information. So you have to label this one as, this one maybe best producers 30 to 40 liters. So at least that way, sense comes in that this is a region, this is the number of animals that are best producers. What do we mean by best producers? They are producing 30 to 40 liters of milk per day in the month of January. These ones will be average producers, that is 20 to 30 liters. Then these one are the poor producers, less than 20 liters. So at least this way, it is easier for one to just have one glance on the drone or on the data, and you get a picture of it for further analysis, as one may wish to do on that. That is our third graph. Let's look at our fourth graph. Our fourth graph, which is the last one, and that is the line graph. Line graph. So we have seen three of them. Our last one is the line graph. And before I look at the line graph, I have now to give some slight difference between these four graphs. The first three graphs give discrete figures. The first three graphs give discrete figures. If it is 60, it remains 60. But it cannot give you a prediction in that graph. You cannot predict if 200 animals were doing this, and out of the 200, 120 did this. How about if I were keeping 300 of them? You cannot easily predict from that graph, which is the pie graph, or even if you are using a bar graph or a column graph. But when it comes to a line graph, you don't always just work with the discrete figures. Out of the figures you are working with, one can easily be able to predict what the other figure can give out as a result. So let's give a representation of the same, then know or understand much better of what I'm trying to talk about. In a line graph, we have two types of lines. There is what we call a straight line, and there is what we call a curve. A straight line and a curve. When it comes to a straight line, we call it a line of best fit. A line of best fit. Best fit means you have several points, but out of the so many points, you get a straight line through the points. On the other side, we shall have a curve of best fit. So this is a line, but in curving mode, such that you follow that curve to get the prospect, or you predict whatever you are after. So let's start with a line of best fit. With this line of best fit, you can have so many plots. Now with these so many plots, they are kind of giving you a direction, but they are not lying on the same line. But from the figures, as you can see, they are kind of communicating one particular aspect. And the aspect is, as this one increases, this one is also increasing in a particular system. So in such a case, you can have a straight line that may pass some points, but leave out some. So it has left out this and this, but it's passing through some. Such a line is called a line of best fit. Now, assuming that we had not done this part, you have only done an experiment, for example, an experiment where you are recording 5 minutes. Hey, boy. Sawa. Sawa. In an experiment where you are recording temperature versus time, you have a solution being created. You had a solvent, you are adding in a solute to form a solution. In it, you have a thermometer to record temperature in respect to time. Every after maybe 30 seconds, you record the temperature. 30 seconds, record the temperature. 30 seconds, record the temperature. You discover that you have only done it for the first 2 minutes or 1.5 minutes, because that is at 0 time, 30 seconds, 60, 90, 120. So this one is giving us at 120, at 90, 60, 30, 0. And you have that. So this is our time, and this is the temperature. So the temperature at this point, let's assume, is 20. Maybe this one is 27. This one is 29. This one is 32. It's not accurate, but it's just a representation. But you will wish to know if this data is giving us a straight line. Is it possible for one to know at what temperature one can get to after maybe 30 minutes? Maybe you are not in a position to carry out the experiment for 30 minutes. But you will wish to know at what temperature will this experiment be after 30 minutes, if it is following a straight line. Is it possible? The answer is yes. Yours is just to draw the graph, which is a line graph. Then from there, record. That is 0, 30 seconds, 60, 90, 120. Continue until you will reach the number of seconds that will make 30 minutes, which will be far away the other side. But since you are interested in getting it, you can use different scaling and you'll still get it fit in the graph. Sorry. From that, you now extrapolate at 30 minutes. From that, get to the temperature, and the answer will be at that point. What you will have done is you have predicted the temperature at which the same reaction will give you after 30 minutes or 5 minutes or 3 minutes, depending on the period you will be interested in. So this one gives us a good idea, the one these other graphs cannot give us. Prediction. Let's look at a graph that is a line, but instead of a line of best fit, we have a curve of best fit. Let's have an example of a graph that is this way. You may not be very accurate. Let's not just assume that we are very accurate. Something like that. So one looks at it, discovered that probably 1 or 2 mistakes were done, and that's why you have such weird figures like this one, this, and this. Then how can one predict the real actual figure that was supposed to be plotted? Maybe it is the same, temperature against time. Maybe we have a temperature that is in degrees centigrade. Remember, units must always be there. Degrees centigrade, time in seconds. So we also have time in seconds. So from there, you create what you call a line curve, a curve line or a line curve of fit, best fit. It must be a smooth one. I mean, because of the anchor, I may not get it very well, but when you are comfortable enough, you can get it. There. So from that, maybe this one was 1 minute, 2, 3, 4, 5, 6, 7. Then somebody asks a question. What could be the temperature? What could be the temperature at the 6 minutes and 30 seconds? At the time of 6 minutes and 30 seconds. And that is at this point. That is not a point you have done experimentally in this experiment. In your recording, as you read the thermometer, record the time, read the thermometer, you didn't have your 6.5. That is 6 minutes and 30 seconds in it. But here comes a question, you have to give a figure. What do? A line graph will solve that problem. What you just do is extrapolate from the time you want, then from there come and get the temperature. And there you are, you will have solved a problem. Now, what have we been doing? We have been doing one essential issue, the issue of communicating. Communicating or communication in science is important in that it makes one to avail what he or she is doing to others for scrutiny, for understanding, or for continuity. It makes whoever has carried out a certain experiment or procedure or whatever to give his or her finding to relevant authorities, since it is something good, a piece of good work done, you avail it to relevant authorities for use, like the things I've just been using to do with the road safety and all that. So as you endeavor in your science studies, make sure that you do proper communication anytime you are carrying out any kind of procedure in a lab, whether indoor lab or outdoor lab. Like the case of the road, that is like being in a lab, but in an outdoor state. As I wind up, After you have done all these work of graphs and all that, as you are communicating your data, in our next lesson, we shall be looking at how to tabulate your recording, how to arrange your recording, how to analyze your recording, how to conclude your recording, so that whatever report you come up with will be a proper communication to the relevant authority. So in our next lesson, we shall be looking at how to write scientific reports for us to communicate properly to the points of authority. Thank you.